In this short screencast, I just want to give you a little bit of flavor of electrochemical cells and redox reactions. First things first, the difference between an electrochemical cell and an electrolytic cell is that in case of an electrochemical cell, there are chemical reactions which produce electricity. So it's the chemical reaction that's occurring which generates electricity. Electricity is going to be generated. So in that sense, you can perhaps consider that this is a spontaneous reaction. Spontaneous meaning it will occur on its own. You don't have to drive the reaction. You don't have to provide any external source for that. On the other hand, if you consider electrolytic cell, you will have to provide electricity, and that will carry out a chemical reaction. So a good example would be that when you have your car battery and your battery is going through a discharge cycle, that means it is being used up. So whether you're honking on the street, or whether you are using it for the light or just movement of the car, you would say that it's essentially an electrochemical mode, or that's how the battery is working. On the other hand, when it is being recharged, so if your battery, the voltage goes down and you bring it to the mechanic shop, you have to recharge it. Or if you need, let's say, jump starting your car, then you will have to provide some charge, and so for the chemical reaction to take place. So that will fall under more of the electrolytic sense. So batteries are a great example of electrochemical cells. Electrolysis, other examples will include things like electroplating. You might have heard of the plated jewelry, which is like gold plated jewelry, or gold or silver plated silverware. And usually what they do is they have a thin coat of silver on much cheaper metals, and the only way you can make it go is by the application of a continuous source of electricity. And hence, in that sense, you say that since you have to provide the energy to make the reaction go, this is going to be called as electrolysis, or the cell that facilitates that is what is called as the electrolytic cell. But either way, the cathode and the anode, which I'm going to talk about in a second, are going to be the same in both the cases. It's just whether electricity is being produced or electricity is being used up in the chemical reaction. All right, let's go forward. Okay, so an electrochemical cell is made up of an anode, which is the negative electrode, and the cathode, which is the positive electrode. You can consider, perhaps, I'm going to pick up what's in your book, so maybe a zinc copper. So your anode is the one where you have placed a zinc strip in a zinc nitrate or a zinc sulfate, that kind of a solution. So it's a zinc 2+, which is present over here. And on the right hand side you have copper, which is immersed in copper sulfate. The neat thing about copper sulfate is that it's a blue color solution. So over a period of time, as copper gets used up in the reaction, you will see a fading out of that blue color. So you can monitor the reaction that way. Notice what's going to happen on the left hand side. Zinc is going to be in equilibrium with zinc ions, and it generates the 2 electrons. Now zinc ions remain within the solution, and the 2 electrons are pushed through the wire, and they go on the other side into the copper strip. That is where copper ions pick up those 2 electrons and become copper metal. So if you think about the basic definitions of oxidation and reduction, hopefully you can see that here you see the loss of electron, and here you see on the right hand side the gain of electron. You know that loss of electron is oxidation, gain of electron is reduction. So you can remember this. Leo, the lion, says grr. And so anytime you're going from neutral to positively charged species, that will be called as oxidation, and positively charged species gaining the electrons to give you neutral atom, that will be called as reduction. Another way to identify oxidation would be gain of oxygen atoms. Oxygen atoms. So for instance, carbon plus oxygen gives you CO2. You say that carbon is being oxidized. Loss of oxygen atoms will be reduction. Loss of oxygen would be called as reduction. You can also take a look at it as increase in charge. Increase in positive charge is oxidation. Decrease in positive charge is going to be called as reduction. So hopefully you can see that on the left hand side at the anode is where oxidation takes place. At the cathode is where reduction takes place. But either way, what you need to know is that the two are going to occur simultaneously at the same time, and in that sense we say that it is an oxidation half reaction and a reduction half reaction that's occurring. And so one can say that half and half makes one complete full, and that's what's occurring in this case also. Now, the species that goes through oxidation, so itself loses electrons, that species is also termed as a reducing agent. Reducing agent. So you would find most reducing agents on the left side of the periodic table. So the species that itself undergoes oxidation is called as a reducing agent. Good examples will be sodium, lithium. Notice they can easily give you Li plus and an electron. It's loss of electrons, so we are saying that itself undergoes oxidation but is going to reduce species around them because it allows for that electron to be given to other species. On the other hand, species which themselves undergo reduction itself undergoes reduction, that is really called as oxidizing agent. And so most nonmetals are oxidizing agents. Great examples will be oxygen itself, chlorine gas. It's used to decontaminate and purify water, and the reason why we are able to do that is because it's going to oxidize the DNA out of the bacteria and hence cleanse it. You might be aware or not, but a lot of cultures in today, even today, use sulfur powder as antiseptic agent. So when little children, for instance, they would hurt themselves, they would just sprinkle a little bit of sulfur powder on the wound itself. And the reason why they would want to do that is because they want to prevent the bacteria from growing. So sulfur powder is used as an antiseptic agent because, again, it's going to oxidize the bacteria in that region and not allow them to grow, and hence allow the wound a chance to heal itself. So just some examples that reflect the oxidizing behavior of the nonmetals. Going back to my electrochemical cells, because that's what I was talking about. Realize that essentially what you're measuring in the electrochemical cell. So I had the anode, I had the cathode, and I had the two metal strips. So these are what are called as electrodes, and they are dipped in an electrolytic solution, an electrolyte, so that's the salt solution. Usually you would find that, so that's the wire that I was talking about. A lot of times, instead of using a bulb, because a bulb just basically tells you qualitatively whether current is passing or not, sometimes they would connect it to a voltmeter. So instead of the bulb, they would put what is called as the voltmeter. A voltmeter is a device which will measure voltage. So realize that the example that I gave you, that was for zinc and copper. And I told you that zinc has a tendency to lose electrons, and copper has a tendency to gain electrons. And at your level, you're not supposed to memorize that. Well, for zinc and copper you should know that, but realize that if we wanted you to work on a completely new system, then we will have to give you more information. But really, it's the ability of an element to go through, and zinc in general will have a tendency to go oxidation better than copper. Overall, if you notice, we have two electrons that are being lost, two electrons that are being gained. So those two electrons are going to get cancelled. Your overall reaction is that zinc plus copper 2 plus gives you copper metal plus zinc ions. That's what's happening overall. Now, if you if you are trying to measure the voltage of the system, depending on the tendencies to give off this electron or to gain that electron, the voltage would depend on that. So we know there's like a boatload of various different batteries that are present in that are available in the market. We have like the really tiny ones that go in your watches and calculators, to the AAA, to the AA, all the way up to the D size. But realize that the voltage that can be produced, it's got nothing to do with the size of the battery. It actually depends on the chemicals, rather. The chemicals that are present in there and the concentration that they're present in. So again, it's the voltage or the strength of what kind of voltage will be generated is a factor. It's a parameter that is dependent on the chemicals used within the battery rather than the size of the battery. And so, for instance, if the application is in something like a pacemaker, so if I wanted to use a pacemaker, you don't want to be changing the battery every now and then. And so a pacemaker utilizes a lithium iodide battery, which generates close to about 2.8 volts, and it lasts like 10 years. So it's the chemicals that are being used in that rather than the size that you have. All right. Okay, now as the reaction occurs, and like I said, zinc is going to give you the 2 electrons and copper is going to gain those 2 electrons. Because of the difference of the potential, notice that the left side of the cell is going to become positive very quickly, and since we are taking away the copper ions from the copper sulfate, maybe, so the right side is going to become negative very quickly, and hence because of the infinite difference in the potential, this kind of a battery is going to shut down very quickly. And so in order to prevent that, we use what is called as a salt bridge, which is nothing but a saturated solution of some kind of an electrolyte. Electrolyte just means that there's an ionic solid, which contains something like, let's say, KCl. And so as you have used up the, or I should say, as you have generated, not used up, as you have generated the zinc ion here, what will happen is that the Cl is going to migrate and neutralize that zinc charge. On the other hand, here the sulfate is getting enriched, and so the K plus is going to migrate over on the right hand side and neutralize and quench that negative charge. So in that sense, you can say that the migration of ions and the movement of electrons is going to facilitate the function of this battery. Now, if you think about the batteries that we need in a car, for instance, those are what are called as the lead batteries. And I don't know if you are aware or not, but your car battery usually requires close to about 12 volts, and even the best lithium ion battery goes only up to about 4. So what actually can provide the 12 volts? Well, each of the lead battery gives you 2 volts. So what is done is 6 of those are put in series so that they can provide an overall voltage of 12, and that is what is used. The electrolyte in that case is sulfuric acid and lead, which is considered a toxic metal. And in that sense, one can say that yes, after the battery has been used up and it can no longer be recharged again, the problem is that it's going to end up in the landfill. And sometimes there are situations, there are cases where there is a leak and leaching of the lead into our environment, and of course that's a problem associated with the lead batteries. But realize that in the charging and the discharging, you can use up a lead battery for up to about 3 to 4 years, depending on your style of using your car. But that's about ballpark the time that you would be able to use a lead battery. Now, if you think about the lithium ion battery, of course that provides you a greater voltage. The problem is that there's always this question whether we have enough lithium to sustain, the requirement for the lithium ion batteries, because everybody wants those. And the reason for that is either A, we do not have a very high grade lithium available, or the areas that it's available, those are really remote areas. So mining it from those areas and transporting it to the battery manufacturers is always a challenge. Other alternatives are fuel cell, for instance. In a fuel cell, of course, you know that water is going to be your product, and that would mean that there's ecologically, environmentally, it's an environmentally friendly version. But anytime you have to use hydrogen, never a very safe alternative, because hydrogen is a great fuel. It really burns very well, and it burns instantaneously, and that's the safety becomes somewhat of a problem if you have to use that in a car, for instance. One thing about batteries, batteries when they are rechargeable, we use the word secondary battery to describe them. Secondary batteries can be recharged. Primary batteries cannot. So what that means is that if you have lithium, which is based on the migration of ions, recall from the book, or if you consider the lead acid battery, which is the battery in your car, or if you consider the NiCad, the nickel cadmium battery, all of those are rechargeable batteries, and hence they will be termed secondary batteries. On the other hand, something like a regular galvanic cell, or an alkaline battery, Leclerc cell, or a dry cell as they're called, the zinc oxide, those are not rechargeable in nature, and hence they will be called as primary batteries.